Delighted to have Henry Jacobs here today. We look forward to hearing what he's going to tell us.
So the title of the talk is Do Particle Methods Make Sense? And I'll just tell you what I think. I think they do make sense, so there's no tension. But to understand why I would even ask that question, I'll start there. So this is based on a paper I've been working out with Tudor, Ratu, and Matthew De Bruyn. So, okay, there's me. And he's here. There's Tudor. And the title of the paper is On the Coupling of an Ideal Fluid and Immersed Particles. And it's to appear in Physica D, but for now there's a preprint, at least at midnight tonight there'll be a preprint on the archive. And so the program, the subtitle is on complex fluids and evolving domains, and particle methods are sort of a natural way to attack these problems in a computational manner, because complex fluids and evolving domains, a lot of times you have bacteria in them or a liquid crystal, or the domain is changing, and in these contexts you are invoking the material representation of a fluid a little bit. Perhaps not the full material representation involving diffeomorphisms, but you're talking about advection of things. And so particle methods seem like a way of dealing with this. Nonetheless, the example I've chosen to attack is a simple fluid in a not evolving domain. But by looking at it carefully enough, you can see how to alter the ideas given here. So specifically, we'll be looking at Euler fluid, incompressible. So, this one. And the type of particle method is more or less inspired by smooth particle hydrodynamics, usually just set as acronym SPH, largely credited to a number of people. So there's Gingold and Monahan. And I think concurrently also Lucy. And they, in a nutshell, what's being done is you're viewing the system as an n-body problem, and you're just finding forces in a sense. It's not quite, it's a little more sophisticated than this, but this is the inspiration for the question I'm about to ask. So, when I say do particle methods make sense, let's compare it with a spectral method. So I'm going to divide the board into two parts. On this half will be spectral, on this half will be particle methods. And we'll do a very back of the envelope comparison on a really large envelope. And okay, so we can view a Euler fluid, or any fluid, as an ODE on the set of divergence-free vector fields, any incompressible fluid. As an ODE on this space, it's an infinite dimensional space, but you can still put some kind of Hilbert norm on it. Hilbert inner product on it. And you can choose a finite dimensional subspace, Vn, say it's dimension n for some integer. And that means then you can decompose it into two parts. And then you can start designing methods on here in hopes that they approximate the exact solutions of the system on here. And because this is in here, you can do these apples-to-apples comparison. And this gives you your error analysis and a number of other, mathematically well-defined tools. Because you can do apples-to-apples comparisons. Try to do this on this thing. One apple minus one apple is 0 apples, but one apple minus one orange is I don't know what. That's all I mean. Yeah. So we're gonna here on this side we're gonna have apple to orange comparisons.
One is to compare results for different ends.
Sorry?
Oh, I'm sorry. I thought one apple would be a given n, and another apple would be a different n.
One apple could be the solution of the Euler-Lagrange of the Euler equations for a fluid. The other apple could be your approximation in Vn. And since Vn is in here, you can compare the two. And this does not work on this side, where we choose the phase space for the n-body problem. This is not equal to this plus or union or Cartesian product with anything. And one way to see this, I hate to invoke category theory, but these are objects in different categories. This is a vector bundle. This is a vector space. They're just different. And if you insist on identifying them, you're going to break something. And so you end up with apple to orange comparisons here. And then the error analysis becomes the question. It's done. Convergence proofs do exist for smooth particle hydrodynamics. There's many of them. But it's not as easy. It's just harder work. Things such as like the order of accuracy of a particle method, to my knowledge, don't exist at this time. But I think they could. And the reason is we don't have to do apple-orange comparisons. I think there is apple-to-apple comparisons you can do for particle methods. So actually, I'm going to use this board because we're going to save this next board. I won't erase for a while. So, okay. So what we normally view the system as an ODE on the set of divergence-free vector fields. And it's easy to forget that this is the spatial representation for fluids. And if we don't, we go back to our continuum mechanics course where we learned elasticity and fluids at the same time. We started up here. We started on the tangent bundle of the set of volume-preserving diffeomorphisms. And then we reduced down to here by using a symmetry, the particle relabeling symmetry, with this map rho. All rho does is it gives you, so rho takes something in here, that would be a phi and a phi dot, and it gives you the spatial velocity field, u. Well, we normally call it u. It's given by just this composition of maps, and we normally call it u when we're over here. In any case, we don't have to forget this. Let's remember it. And we'll start up here again. And instead of coming down to here, which we got by reducing by the particle relabeling symmetry, that means reducing by this group here, we could have reduced by a different group. So there's some other group which I'll introduce soon, which we could reduce by, and it would bring us to a different space, in particular a vector bundle. And what's noticeable, so this is a direct sum of two vector bundles. The first one is the phase space for the n-body problem. And so now, if we could get over to here and get our equations of motion on this space, we can start doing apple-to-apple comparisons. And then the only difference between this space and this space, well, there's many differences actually, but the particular difference in terms of just the data stored is this space has n labels for the particles. This has no particle labels. It just has velocities. So all you have to do to get down to here is you forget those labels, and that means doing a reduction on the set of labels, which means reduction by the cyclic group on n elements. So I think what I'll do next is I'll review this picture so that we get comfortable with the material representation. And then I'll do this picture. So let's do this first. So on this side, we'll have the material representation. I'm doing this more to just set up the notation. I know it's known, but on this side, we'll have the spatial representation. So on this side, we view the state of the system with a curve in the set of diffeomorphisms, volume-preserving diffeomorphisms of your manifold M. And the equations of motion will be Euler-Lagrange equations with respect to some Lagrangian. For an Euler fluid, capitalize. For an Euler fluid, you take a phi and a phi dot, and you just calculate the kinetic energy. That would be the Lagrangian for an Euler fluid. And then you get your Euler-Lagrange equations. So the equations of motion are assumed to be the Euler-Lagrange equations. I won't write them down, but this means hypothetically, you could solve these equations. Not really, but you would get a flow map on this tangent bundle on the space of diffeomorphisms. You would get a flow map, as you do for any ODE. And all the flow map does is you give it an initial configuration and an initial velocity, and it will give you the configuration and velocity at time t obtained by the evolution of the Euler-Lagrange equations. And then on the spatial side, things look different. We have a time-dependent divergence-free vector field. And the equations of motion are, for example, for an Euler fluid are this. And hypothetically, you could solve these equations, at least in local time, and you would get a flow map, which goes from initial vector field to a final vector field in the current configuration. And what it does is it gives you take a u0, an initial velocity field, and it'll give you u at time t obtained by evolving the system under the evolution of the inviscid fluid equations. And then the connection between here and here is given by this map rho, that map rho on the far, far, far left. And this picture was further clarified in the context of Lie algebras and Lie groups by V.I. Arnold in 1966. So I'll review V.I. Arnold's discovery in 1966. I suspect he made many discoveries in 1966. I'll review one of them. which is, well, firstly, let's write this picture very succinctly. What I've just said is that the following commutative diagram is a commutative diagram. It commutes. So what this diagram says is that you could take the flow in the material representation and then trivialize it, get the vector field that pops out at the end. Or you could trivialize it at the beginning and then take the flow of the inviscid fluid equations and you get the same thing. And what this diagram in some kind of meta way says is that these two flows are doing the same thing on different spaces. And they're connected through the map row. So, I mean, of course, that's not all he did because this was known. But what he also realized was that these inviscid fluid equations could be written in terms of concepts which are defined on general Lie algebras. Because this thing here is a Lie algebra. In fact, this is the Lie algebra of this Lie group. Well, of S-diff as a Lie group. And he found out the equations could be written this way. ddt of dl du, where L is the kinetic energy of the fluid. U is the, well, you know what U is equal to minus add star U of partial L partial U. And so I know that not everybody in the audience is so comfortable with using this wacky notation, but the takeaway message is that the Lie algebraic structure of X-div does come into play if you want to understand the inviscid fluid equations, or it could come into play. It's one way of understanding them. So that more or less completes this direction. Now we're going to go this direction and kind of basically do V.I. Arnold 1966, but with a different group. I mean, it's notable that this vector space here can be written as a quotient of two spaces. And I know dividing a space by a space might not sound very appetizing, but it's not as bad as it sounds. Yeah, actually, I'll give you examples of what a quotient means. I won't define it formally because it's hard to swallow the first time you see it if I define it formally. But the big idea is pretty easy to swallow. So let me give you two examples of quotients of one space divided by another space, specifically a space divided by a Lie group. So let's take the space R3. The set of rotations is SO3. It acts on R3 by rotating points in R3. And we say that R3 modulo SO3 is just, typo. Is just the set of positive real numbers. How did I get this? And the map that goes from here to here is just you take the magnitude. Okay, so how do you go from here to here? Well, R3 consists of things with direction and magnitude. SO3 changes the direction. So R3 modulo SO3, all that's left over is the magnitude. Basically, when you have this group acting on this other space, if you have all the elements of the group act on it, you remove a bunch of data, and what's left over is called the quotient. The other example for us is TS diff, the set of volume-preserving diffeomorphisms. The set S diff acts on TS diff. So TS diff consists of particle labels and their velocities. S diff acts on it by relabeling the labels. So TS diff is a quotient over the set of this, well, is a quotient over this quotient space. Sorry, TS diff is a bundle over this quotient space. The quotient space being, well, you can write it as TS diff m divided by S diff m. And of course, this is equal to something much more concrete than what's being written on the left. It's equal to the set of divergence-free vector fields. And this is because when you have these things relabel the labels, this thing consists of labels and velocities. So when you consider all possible relabelings, the only data that's left over is velocities, and thus you end up with x div. That's sort of the idea behind quotients of spaces by groups. You remove data. Okay, so now we'll talk about removing a little less data than this. We'll use a smaller group, and we'll remove less data, which means more data will be left over in the quotient, and we end up with this space. Sorry, I shouldn't have used this board. I want to use this board because I want to save it and not erase it. So let's construct a Lie group. It's going to be a subgroup of the set of volume-preserving diffeomorphism. So fix a bunch of points zi in M. Perhaps there's capital N of them. And then set gz is going to be defined as the Lie group given by all the volume-preserving diffeomorphisms subject to the constraint that psi does not do anything to these chosen points. Distinct. Make sure they're distinct. And then okay, so this is a Lie group, or at least it's a pseudo-Lie group. It's as much a Lie group as the set of volume-preserving diffeomorphisms is. And you can calculate its Lie algebra, which I'll denote with this G with a little bar in it. So the Lie algebra, it should be a Lie subalgebra of the Lie algebra of S diff. So it should be, it should be a divergence-free vector fields on the manifold, subject to the constraint that U evaluates to 0 at each of the points. And then just to check that we're on the right track, let's calculate a quotient space. So if we look at the set of this group, S diff M, and we quotient it by a subgroup, GZ, we get a homogeneous space. What is the space? Well, this does a lot of relabelings, except for it doesn't change the label for these guys. So all that's left is basically n points in M. Oh, and they're not overlapping, so I'll put a little tilde to say that they're not overlapping. And this is the configuration space for the n-body problem. And then one last bundle to at least write down. So this is a vector bundle over this space, and it's given by pairs of x's and v's such that x is in a bunch of particle configurations, and v is a divergence-free vector field, and v is subject to the constraint that v evaluates to 0 at each of those particles. X is a tuple, an n-tuple of particles. Okay, and then finally, you should choose a map I. This is a choice. Choose a map I, which takes some particle velocities and gives you a divergence-free vector field on the entire manifold. And we call I an interpolation method for, well, you know what an interpolation method is.
Where does the relabeling symmetry here in the G sub, well, in either big G sub Z or little g sub Z? And I would have thought that relabeling might, for points, might permute the points around, but leave the leave the positions of those points alone. Yeah.
Yeah, so
But
this is the group that relabels, basically, this group relabels all the points of M except for these Z's, which we're choosing to be fixed.
It relabels all of them, or does it just relabel those on a specified curve or something like that, as you would have for circulation?
I only see one constraint here. This is the only thing that makes it smaller than relabeling all of them, which would be the entire group S diff.
But the Euler equation has infinitely many constraints because it has all the curves that you can draw, the circulation is conserved on them.
Yeah, so when we reduce by this group, we won't get the full Kelvin-Noether circulation theorem. We get all curves that don't intersect a finite set of points. It's a little smaller.
So does that psi of Zi equals Zi mean that the set of particles is left invariant, or that each point is left invariant?
That the set of particles which are fixed, so this is outside of the definition of GZ. Yeah, there exists a bunch of ZIs which are left invariant.
What is a set? That was it.
Oh, I see. Right, point-wise. Right, the order matters. We don't permute them, which is why I have this extra reduction to do here. Thanks for clarifying. Okay. So I is an interpolation method, and it is what it sounds like. What you do is you give it two velocities. I will give you a velocity field, which spits out those two velocities, and also interpolates a smooth velocity field on the entire space. And then given this map I, which you've chosen, perhaps arbitrarily, you can define another map rho I, which is important because it's going to appear right there. Rho I, and it goes TS diff to the phase space for the n-body problem plus this other infinite dimensional vector bundle. And what it does is you feed it a material configuration and material velocity, and it will spit out, well, first you have to get something in here. So what you do is you have phi dot act on z, or all your zi's, and you get a bunch of particle velocities. So you get elements in here. That's the first component. The second component should be a vector field which vanishes at phi of z. So first thing you do is you take your spatial velocity field. This is u normally. This will not vanish at phi of z, and from it you subtract whatever your interpolation method gives you. Okay, so this is I outputs vector field, so we're doing a vector field minus another vector field. We get a vector field which vanishes at phi of z. Okay, so something to note
Would things change very much if it wasn't incompressible but was slightly compressible?
I don't imagine so.
I don't think so.
Yeah.
I think you could generalize it.
Yeah, change it from S-diff to diff. Yeah. I stuck with S-diff because I wanted a nice example to shoot towards, and I chose the Euler equations. Okay, so some observations. The first one is that this space here is identifiable with this quotient set. Second observation is under this identification, rho I is the quotient projection. It's precisely the map which throws away the data of all the particles that are not Z, that are not labeled by Z's. The third observation is that because, we already, it's been verified over and over again that this system has S-diff M symmetry. If it has S-diff M symmetry, it certainly has symmetry with respect to any subgroup of S-diff M. GZ is a subgroup of S-diff M, thus we have a GZ symmetry, and thus we should be able to go from here to the quotient, the quotient T S-diff M modulo GZ, which I've just stated, I didn't verify it for you, is just this set here. So there should be equations of motion on this set. So there must exist some flow map FT such that the following diagram commutes. I'm trying to make it look a lot like this Arnold 66 board. So we have the original flow of the system, which is in the material representation was given by capital F, and there must exist some flow on here on this reduced space, which is up to a phase equivalent to the flow upstairs. Okay, so now you can ask if we have a flow, we should have some equations of motion. What are the equations of motion?
Little f is the flow of particles, is it? The bottom flow.
Little f is the flow of particles plus n, this infinite dimensional object we have to carry with us.
In that space, everything is discrete.
In this space, everything is discrete, and then this consists of vector fields still.
Mm-hmm.
What's kind of nice about this splitting is you might want to think of this as say you did have a particle method. Your error analysis should consist of you analyzing how the dynamics in this space are being ignored. This in some sense contains your error.
Usually the problem with trying to find the errors in a method like SPH is the fact that the errors depend upon where the particles are. And you don't know that until you run the calculation.
Mm-hmm. Yeah, right. So this space, this is a vector bundle, not a vector space. It's a bundle over something. What is it a bundle over? It is a bundle over particle positions. So it seems to be respecting this difficulty. Okay, so let me give you equations of motion for this flow. The way that you can get them is by doing what's known as Lagrange Poincare reduction. And it is in some sense, it's a generalization of this reduction done here. And my source, where I learned about Lagrange Poincare reduction, was a book by Hernan Sendra, Gerald Marston, and Tudor Ratu, called Lagrangian reduction by stages. It's a thin book, but it's heavy. But if you get through basically chapter 1 and chapter 2, you will see some equations of motion. And these are the equations of motion. So the first thing you have to do is define what's called the reduced Lagrangian. It is a function on this space, and in the case of a fluid, it's just the kinetic energy, but written in terms of objects on this space. Formally, L is defined by this relation here, where L is the Lagrangian of your unreduced system. And for example, the reduced Lagrangian for an Euler fluid is given by the following expression. So you take particle positions, particle velocities, and some v. V is not the spatial velocity field of the fluid, but it gives you it. And it outputs the kinetic energy, but written in terms of these objects, the kinetic energy is given by this. You take your interpolation method, apply it to x and x dot. This gives you a vector field. To this vector field, you add v, and then you take its norm. And you integrate. And this gives you the kinetic energy of the fluid. In any case, whatever your Lagrangian is, your equations of motion can be written down on this space. This will give you, on this space. And this space has two parts, 1, 2. So I'll write the first part first. This is the equation for on Tm, on the phase space for particles. It looks like an Euler-Lagrange equation. Except for there's this irritating coupling on the right-hand side. And then on the bottom, on this space here, the equations look a lot like the way Arnold wrote the equations for an ideal fluid. It's no coincidence. Because if you had no particles, the only equation you would have is this one equation, and you better get the right answer. Anyway, so this one is on the phase space for the n-body problem, and this one is on here. And if only we could ignore this guy, we would have an ODE on this space, and that would give us a particle method. So deriving particle methods, and one could start deriving particle methods by finding clever ways of ignoring this guy, or at least finding ways of bounding your solutions away from the exact. So I could talk about. Okay, so I'm almost out of time. So what I'm going to do is I'll talk about one generalization which allows you to look at fancier particles.
But can I ask a question first? If we look at the square of the sum.
Of what?
Okay, in the kinetic energy.
Okay.
Okay. So we take the variation with respect to v. Okay, and we get I x dot plus v. Okay, that goes downstairs.
Mm-hmm.
Now we take the variation with respect to x dot. Okay, and we get the same object, but with one operator acting on it makes it different.
Mm-hmm.
Is there any more information in that than in the first variation?
So for one thing, yeah, it's independent information. The reason being, V is restricted to be in here. That restriction means you take variations that are in this space. And so these guys are, it's almost equal to U. It's almost equal to the spatial velocity, or the momentum. Except for you have this one constraint, so the momentum have this extra constraint.
I'm just thinking of the algebra. If I take variational derivative, I get I of x and x dot plus v.
That's right. dl dv is going to be I of x dot plus v.
And what puts it into the Lie algebra?
It just, well, you have to think of this, don't forget that this should be a covector. This is really in the dual space.
Okay.
It's going to act differently than the normal fluid momentum because of that. If you view it as a true like covector field, you should view it as a covector field restricted to this space, this subspace. So this contains less information than the full spatial velocity field in that sense, at least formally speaking.
So, but the interpolation also contains less information, right? Because it's reconstructing the full flow from a few points of, a few particles.
Well, okay, we can describe exactly what information is here and what information is here. What information is here, since I is above each x, I is linear. It is injective, and thus it is bijective onto its image. So the only information that I contains is the particle velocities. The only information that I of x dot contains is the particle velocities. V contains all the other velocities except the particle velocities. It's independent in that sense, right?
But if you just follow the prescription of SPH, you would find that you have to interpolate anyhow, and therefore, dependent upon the scale of the interpolation, which is kind of like the spacing between the particles, you lose all information which is below that scale. I mean, that's what interpolation does. I mean, there's a scale below which you don't have things. So you miss out on short length scale phenomena.
I mean, I would say, like, I haven't chosen, I've basically been playing games with simples, and I haven't made any real assertions yet, because this is just, when you get down to it, is just identical to the fluid equations for an ideal fluid, plus you add a bunch of labels to them. And so, perhaps the name of the game for deriving particle methods such as SPH is choosing I. I've written down something for a general I.
Yes, well, with SPH you can do it two ways. You can write down Lagrangian, like you said, but discretize it immediately. Or you can write down the equations of motion and ask yourself, how do I get grad P? Because once I get grad P, I know the acceleration, so I can start moving. I can see how the velocity changes. As it turns out, both give you the same result, but I don't see at the moment how this fits in with this, but I think it does.
Yeah, ditto. Let me describe a way to jazz this up a little bit, and then I'll stop. So when we reduce by this group, we notice we got particles. If we reduce by a smaller group, this quotient will get larger, and we'll get funkier particles. So what you could do is look at this constraint here and make it even more constraining to get a subgroup. In particular, this constraint, you can read it in words as saying that psi is the identity to zeroth order at the particle locations. Let's make it the identity to kth order. So the way you write that down is you use something called a higher order tangent functor centered at the particle locations. And you say that whatever this thing outputs, it should be equal to whatever it outputs when you applied it to the identity. Formally, this just says these guys have a Taylor expansion equal to the identity at the particle locations. Okay, and the resulting Lie algebra can be written down in a way that's perhaps more concrete than what's written here. So let's say you have some local coordinates. The Lie algebra just says that if you take its partial derivatives, alpha is a multi-index of these vector fields U, and evaluate them at the Zi, you should get 0 for alpha less than or equal to k, for the rank of this multi-index less than or equal to k, where k is fixed. And we'll call this group gk, and its corresponding Lie algebra will be little gk. And this quotient here we'll call mk. And our interpolation methods are now kth order interpolation methods in the sense that they respect the data up to kth order now. And you can play the same game and you'll get a different set of equations of motion, except for you'll be on this quotient space with these jazzier particles. So let me just tell you what these particles are for a simple case. Let's say M is the 3 torus. Then, for example, M to the n tilde 1 is going to be the following Cartesian product, n-fold Cartesian product. It's just going to be, well, okay, you take points, so a point in your manifold, and attached to each point, you have a little matrix, an element of SL3. And this allows you to have a first-order description of the shape of a particle. I'll do one more. Mn2, oh yeah, and the particles can't overlap. Mn2, well, you have particle positions, you have their first-order descriptions of shape, and you also have second-order descriptions of shape. And then the last thing to note that's kind of cool is that this is a group. SL3 is a group. This thing here, if I write it correctly, is a semi-direct product of some sorts. It's also a group.
Henry, when you use the word shape, is that in the literal sense of the English language, or is it technical meaning? I mean, can it be kind of banana-shaped or spherical? Or?
An element of SL3 describes, let me think about this. Out of SL3, you can pull 3 axes, which represent the principal axes of an ellipsoid.
Yes. So it certainly can prolate or oblate.
So it could be concrete. And this, I don't have a name for it like I do for SL3, but I can best describe these as second order. These are kind of like linear descriptors of shape,
Yes.
and these are second order. And what's notable is that this is a Lie group. This is a Lie group. If your particle method, well, if your original ODE, say it's the Euler equations for a fluid, have a full symmetry, have a full S diff M symmetry, then you should have, and then the reduced system should have the following symmetry. It should have GZ modulo GZK symmetry. Because we've reduced by GZK, but we have extra symmetry, which we didn't reduce by. This is the leftover symmetry. And for k equals 1, the symmetry group is SL3, and for k equals 2, the symmetry group is the semi-direct product. And the point is that this, I mean, just looking at the particles that pop out, you can kind of see how Kelvin's circulation theorem could actually enter your particle method, because your particle method now has a group structure to it. And it'll be a Kelvin circulation theorem. Of course, it's on a finite dimensional space, so you have finite dimensional conserved quantities. And in pictures, what those conserved quantities should correspond to. In the original Kelvin circulation theorem, you can take arbitrary curves, and the circulation along the curve should be constant. In this case, we take curves that are infinitesimally close, in some sense, to these particles, and circulation of these infinitesimally close curves should be constant. This is the particle-centric version of the Kelvin circulation theorem.
Uh-huh.
Right.
So how does the SL3 part enter the Kelvin circulation theorem?
Well, the way that you're going to talk about the circulation now corresponds to how fast this particle is changing its SL3 component.
Okay, so circulation has more components. It's not just position, but some kind of change of shape. It's also part of the circulation.
Yeah. But that's how it is in SDiff also. You have a curve which can change shape and whatnot.
Well, if you had that curve,
And this one, I'm only looking at the curve to first order. So it's described by a linear transformation.
can I just say that if that curve was not a continuous curve but a necklace, and each bead on the necklace was actually a particle, not quite enough, but that will do, then your Kelvin circulation theorem is a relabeling along that, just shifting them around and changing velocities and positions. And if you've got bananas, you have to actually rotate the bananas so they're lined up with the position of their neighbor.
When
And
you
do
say
that
bananas,
round-
you're thinking of SL2 things or something?
I'm not sure what space I'm thinking of. I'm just
Okay.
thinking of a little necklace that passes through a set of particles.
Okay.
Now, if you want to keep the system invariant, then you have to think of a transformation which shifts, say, the bottom one to the position of the other one, gives it its velocity, and rotates it so nothing has changed.
Right.
And then you get the one that was there, and you shift that round.
Yeah.
So actually, you get two contributions to the invariance.
I mean, this version of a circulation theorem, which you're talking about, is quite different from the one that's being described here, in that you're considering necklaces over finite different distances.
Yes.
And I'm doing infinitesimal things.
Yeah, I see that. The result is that the circulation theorem is a non-theorem for this strictly,
Yeah.
because it's discrete. So Noether's theorem doesn't apply. But if the velocity field and the other fields vary slowly on the scale of the spacing, then it becomes progressively more accurate. And when you do a calculation and follow loops, you find actually that it is quite accurate given those assumptions. Well, somehow or other these have to all be the same.
I think these ones will not be. This one, you have a circulation theorem before you even go to a large number of particles. This one, you'll have a circulation theorem for one particle.
Yes.
So this one should converge to this one as the particle.
Indeed, it should.
Yeah.
Indeed, and I think it's possible to prove it does.
I see. Okay, well, that was my last
And
one.
it's an error. I don't know if it's an apple-orange error or an apple-apple error, but there's an error.
Yeah. Okay,
Finish?
that's...
Yep. I think we're finished.
No questions?
Go away. There might
Don't
be
go-
questions.
Well, you can use particle methods for, say, elastic bodies. So the particles are carrying other stuff around like tensors. But that doesn't change anything, does it? The way you formulate this. The particle's got a velocity, it's got a position. It might even have a composition. And then it has some other quantity which is not a scalar, it's not a vector, it's a tensor. But that doesn't matter in your description, does it?
No. Well, like I talked about this Kelvin theorem at the end, so that will disappear
Yes.
if you don't have that same symmetry. That's a good thing. I mean, if you're doing solids, say, solids don't have that symmetry. If you had it, you should be scared.
Right. And I noticed you never mentioned boundaries. Is that deliberate because they're just trivial?
No, it's the other way around.
Uh-huh. Right. Certainly, I was at a conference in Norway a week or so back, and there the marine engineers worry with their particle methods a great deal about the boundary, whether it's actually with the particle methods, free surface boundaries are easy, but there are complications with other boundaries.
I mean, formally, I've not put anything into a computer, so I can't vouch for these ideas. But formally, when you choose that interpolation method I, the things that are output should be tangent to the boundary a priori, and so the boundary conditions that you deal with in SPH, where you're afraid of particles leaving, and so you have to align the walls with particles.
Well, you don't actually have to do that. I mean, you may have a free surface. It might be like the water that's in that bottle. I think there's water in that bottle.
Mm-hmm.
And so it has a free surface and side boundaries, and you could take the top off the bottle and pour it into that other container, and it meets new set of boundaries.
These type of boundaries. Yeah, no, I didn't address this at all. And the structure changes a lot. I mean, I can think of a way to do it, but it's not.
I think it's an interesting and important problem. And if you solve it, many people will be happy.
Do you want to say something about the force on the right-hand side with that B?
The B, sure. So the B is known as a curvature tensor, and what it is not as important as what it means. In some sense, it manifests the following fact, which is that the vector fields that are output by this I, assuming you have more than 3 particles, say, are going to be, they're not going to form, the range of I is not going to form a Lie algebra. It's not going to be closed under the Lie bracket. And this non-integrability has to punish you somehow. And this is how it punishes you.
It's not exactly punishing you, it's telling you how the particles move in response to the fluid.
Yeah, I guess it's telling you the truth. I guess that's not a punishment. It's just the sad truth.
When you use SPH for the driving term, you get some pressure terms and density terms. And you've done some interpolation using kernels, so it depends upon the coordinates. But you need all that because when the particles move, they change their positions, and you need to know about their effective density.
Right.
So somehow or other, that also, I think, is in it. But it comes automatically from the Lagrangian. If you give me a Lagrangian, I can write down the equivalent particle method.
But your method would be on T of M twiddle N.
Yeah, you mean if I give you a Lagrangian on which space? On
Well,
T or so on?
just give. I mean, you give it. For me, it's a Lagrangian R3. So you just got some energy terms, kinetic energy and maybe an elastic energy or something else. And you might give it to me so it's an integral over the space, and I'll immediately discretize this, and then I'll just write down the equations of motion. More or less, end of story.
But what the equations of motion you write down, now you can subtract them from those equations of motion.
When you say
You'll write equations of motion on here.
Yes.
After I give you some Lagrangian,
Yes.
and then you and I will wonder, like, is this a good simulation? And we can answer that question to some extent because we can subtract it from these equations of motion, which are the exact ones.
Yes.
So the term on the right-hand side would be an error term for Joe's calculation. And it would be coupled...
Or it would be one component, yeah.
One component. And it would be coupled to this other space, which is moving.
Yeah,
Yeah.
that's right.
Because I have to get a grad P. How do I get a grad P? I've just got n particles.
Yeah.
Yeah, so I need to get a gradient. But of course, what you do is interpolate the pressure from the particles in a particular way, which is well prescribed. And that gives you the pressure everywhere, which you then just differentiate.
Mhm.
That's the source of error, or one source of error. The fact that you've had to go through that machinery.
Okay, so I should learn this from you.
You could easily learn it from me. If we stick here for another half an hour, I could put it on the board, but I won't.
But can't you know, in the continuous case, you get the pressure by imposing incompressibility. Isn't there some analog of incompressibility in the Lagrange to Euler determinant of the Jacobian is equal to 1? Isn't there a discrete version of that you could put into the Lagrangian as a constraint, and then then the Lagrange multiplier would be the pressure?
Yeah, it's a bit it's a bit complicated to include this because it turns out you have a Lagrange multiplier for each particle.
I mean, if you were willing to use these particles, the incompressibility constraint is here. And the fact that you're considering SL things for your descriptors of the shapes of the particles, that's not what you're asking for, though. You're asking for an incompressibility constraint on just here.
Yeah. So
The-
there would be a pressure at each particle, just like there is a pressure at each point.
Yes, well that's true, and there are two approaches to it. One is to assume the fluid is slightly compressible, and it turns out everything's easier if you've just got slight compressibility. On the other hand, there's an error from that. Or you could insist that div v vanishes at each particle, and then you have some expression for div v. And in the end, what you're going to do is you're going to get a Lagrange multiplier for each one. And then there are some other methods, shake and rattle methods, which are used in molecular dynamics, which are also used in that context. But actually, the simplest one is no doubt to treat it as slightly compressible. Then you give up then you have a density which varies slightly. And if you want to find the pressure, you have an equation of state. And look, it's easy to write everything down. And then it's easy to solve the fluid dynamics of what happens when you pour that bottle into the other fluid into the other container. But when you have a look at the errors, you think formally the errors should be, say, second order or something higher order. They turn out not. They're somewhere between linear and second order. And that's because of the disorder that's created from the particles. So when I interpolate to get the pressure, if the particles are disordered, then that interpolation has errors that depend on that disorder. That's kind of obscured in this, but in practical terms it's there.
Yeah. I think, if I'm to understand this, I have to start from, R3 and...
Yes.
I don't think starting from here would be a good idea, but then we could probably get to here. I mean, ultimately, at the end of the day, we should get to here because these are the equations of motion for any manifold.
Both approaches are I think, are valid mathematically, given certain errors that may occur. So if they're valid mathematically, it must be possible to see how they fit together.
Any other questions? Well, thank you again.